Hi, I'm Michelle, a graduate student at Carnegie Mellon University. I'll be presenting our work titled Coordination via Strategy Matching. When performing collaborative tasks, teams may approach the task in different ways. For example, when cooking with others, people may specialize in a particular role or subtask, or they might jointly complete each part of the task in order. Poor coordination of strategies can lead to inefficiencies. Robots designed for collaboration must be able to coordinate by inferring their partner's strategy from their actions. With the goal of enabling robots to better coordinate, we explore the following question. How can robots identify and match the strategies of human partners? A useful domain for exploring strategies on collaborative tasks is Overcooked, a simulated joint cooking task. The objective is to prepare an order and serve it as many times as possible. We use the test bed and dataset developed by researchers at UC Berkeley. The dataset contains demonstrations of two-person teams performing the task in 5 different environments, for which the kitchen is laid out differently in each. The layout helps to dictate what coordination strategies are available. In this presentation, we'll focus on the environment titled Forced Coordination, where a barrier in the middle of the kitchen necessitates that the partners coordinate to complete the task. One strategy that teams may take in this environment is prioritizing serving a dish immediately when it's ready. Another way in which teams may approach this task is to make full use of all kitchenware available by making sure that both stoves are utilized. We can see that the approach to coordination prescribes the order in which tasks are performed by each partner. Thus, we define collaborative strategies at the team level as the sequence in which high-level tasks are interleaved and distributed across teammates. In this work, we develop a method for recognizing and adapting to partner strategy, which we demonstrate on an Overcooked agent. In order to be able to coordinate, robots must first identify what strategies exist in a given task environment. Next, they must learn to partner proficiently with different strategies. And when working with new human partners, the robot can then use what it's learned to adapt online. We will next step through these 3 components in greater detail. We begin with a dataset containing team trajectories, which are high-level action sequences. We will illustrate the approach using 6 team trajectories. Each partner's actions are represented in blue and yellow. The robot does not know a priori what strategies exist for performing the task, nor how many there should be. Since there are numerous possible subtask orderings, we'd like to maintain a tractable space of strategies to reason over. As such, only orderings that differ significantly should be classified as distinct approaches. Thus, we frame strategy identification as an unsupervised learning task of recognizing distinct patterns in the sequences of joint actions. First, we train a hidden Markov model on the set of team trajectories. Using the learned parameters, we compute the most probable hidden state sequence for each trajectory. This gives us a low-dimensional sequence representation. Next, we perform k-means clustering on the set of low-dimensional sequences. We selected the combination of number of hidden states and clusters achieving the highest silhouette score. Each cluster represents a strategy where human teams in a cluster coordinate in similar ways. Now that we've identified primary strategies, we aim to construct a library of robot policies trained to proficiently employ each one. First, we train a model to imitate a human partner performing each identified strategy. The model is trained using behavior cloning, with fine-tuning on the subset of teams in the particular cluster. Next, we learn the reward weights corresponding to each strategy using maximum entropy inverse reinforcement learning. In training, the robot policy learns using proximal policy optimization to partner with a human proxy employing a given strategy, while maximizing the strategy-specific reward. Finally, when collaborating with new partners at test time, the task of the robot is to recognize and match the partner's strategy online. Each strategy is weighted by how accurately the policy predicts actions taken by the human partner. The robot updates its belief weighting over strategies whenever the human takes an action. Robot actions are then sampled from a weighted combination over action distributions proposed by each policy. This online adaptation framework allows the likely strategy of a player to shift as the episode progresses. We ran a user study to compare our approach, abbreviated MESH, to an existing baseline agent. The baseline was non-adaptive and was trained by partnering with a human model trained on aggregate data. Focusing on the force coordination environment, we found that our approach improved task performance measured by the number of orders served in a 60-second round. We were also interested in how the agent affects team collaborative fluency, meaning how well members in the team were able to coordinate their joint activities. Concurrent activity is the amount of time in which both teammates were working simultaneously. We found that this was higher in teams with the mesh agent. Relatedly, the mesh agent spent more time working on the task, meaning it was less idle. Participants also self-reported higher collaborative fluency in their interactions with the mesh agent. Our study results overall show that an agent designed for coordination on strategy may improve task performance and interaction fluency. However, the improvements vary across environments. Our approach improved team task performance in 2 of the 5 environments, and improved interaction fluency in approximately 3 of the 5. In other environments, both agents performed comparably. This suggests that the layout influences what task approaches are available, and differences in salient approaches may influence the efficacy of our method. Understanding how the differences between layouts affects potential strategies is part of our future work. To conclude, focusing on strategy coordination may help robots reason about how their actions interplay with the behavior of team members. And this work explores an approach for identifying and adapting to different coordination patterns. Thank you.